Good afternoon, everyone. This afternoon, you have been hearing about a lot of different applications, thermography applications, and as much as optical gas imaging is a type of thermography application, there are a couple of things that set it apart from the other techniques you've been hearing about today. So I'd like to talk a little bit about what makes it different before I go on to show you some examples of the different types of applications for optical gas imaging. So how does it work then? The gas cloud absorbs the radiation. Here's our radiation going through our gas cloud and into our camera detector. So the radiation is absorbed before it can get to the camera detector. So we are blocking that radiation from getting to the detector by the use of a filter. So we match the spectral response of the camera to the peak spectral absorption of the gases that we're interested in. So there's several different filters for different gases. In this case, for all our VOCs, our peak absorption is approximately between 3.2 and 3.4 micrometers, as we can see here. So when you have a positive background energy then, so that is more molecular movement, a hotter background, if you like, then the gas cloud absorbs that energy coming from wherever it's coming from, not allowing the energy to get to the camera detector. So this is giving a negative response, and that is produced in the form of a black cloud, depending on the settings of your camera. In contrast then, when you see a white cloud, it's a similar scenario, but when you have a negative background, so here we can see less radiation, the sky is a good example of a negative background. It will always give us a cooler response. Then the gas cloud absorbs the emitted energy. So either way, the camera will be able to visualize the plume, the gas plume. So to break it down then, we've got a simple diagram here. We can see this is our radiation coming in, our cold spectral filter here. So our filter, in actual fact, is a coating on a lens. Once the energy or the radiation has been filtered, you can see that it's reduced down. And this area here is our cold finger or our cold shield. And here we have our detector. So the energy goes through the lens. The filter maximizes, the filter limits the energy. The cold shield maximizes the NATD, the noise equivalent temperature difference or sensitivity, giving the camera the ability to detect incredibly small emissions. Now, this area in here is cryogenically cooled down to a temperature of approximately minus 196 degrees C or 77 Kelvin. So very cold. And what this does, it reduces the noise and allows the protons to jump across without any background interference. Here we have a picture of our coolers. Rotary coolers are the most common for the handheld OGI cameras. I think to date, they all have these types of Stirling cooling process. So here we have a piston, rotary piston, and the Stirling process removes the heat from the cold finger, and it dissipates it out the back of the detector to try and keep it as far away from this area, which allows us to keep that, to maintain that cryogenic minus 196 degrees C. It's not particularly efficient, but it's good enough for infrared camera detectors. The drawbacks for these coolers are they are noisy. They do have, because of the design of the cooler, they have some mechanical wear, seal wear over time because of the vibration and mechanical movement. So they're not perfect, but they do the job. We have Flower's latest offering. It's called a Neutrino. Now, this one is a linear cryo cooler. So they've ironed out some of the problems of the previous coolers. Now, these ones are more modular integration. They're smaller, more lightweight. They have predicted significant longer lifetimes because of the lower vibration, etc. Larger cooling capacity in here, and it does tend to make them take longer to cool down to get to their cryogenic temperatures. But that's the only real drawback. So they come in a variety of different lens configurations. Here we've got a couple of examples. Still medium wave, of course, photon detectors. And because they're small size and lightweight, they're already being utilized and integrated for using on aerial platforms, so for drone cameras and the likes. So, like the things we require then to see gas with the camera, this is the thing that sets it apart really from all other infrared cameras. So kind of like the fire triangle, we have the OGI triangle. We've got the wavelength. The gas must have an absorption peak that overlaps with the spectral window of the camera. The delta T, so there must be a sufficient temperature difference between the gas plume and the background. A reported minimum of 2 degrees, but of course, the greater that difference, the better. And our gas, of course, there must be a gas present in the image that's greater than the minimum detection limit of the system. Now, different gases have different limits, but as low as 3% of any of the gases the camera can see will give you a resolved image. So most gas leaks can be detected with, as I said, a minimum of delta T of 2 degrees. And here we can see an image of a nicely optically resolved gas plume. So response factor, that's our wavelength. For propane here, we have a minimum detectable limit of 2 liters per minute. Methane is 16, so it's a reasonably low amount of gas. You can see the difference between the two there. So quantitative optical gas imaging then. What is it? So the delta I is the change in intensity at a pixel level as the pixels move across the field of view. So basically the camera is counting the pixels and doing a fancy algorithm to give us a response or a result. So why would we use this technique over any of the other available techniques on the market or more traditional techniques? So, well, for one, you can see the leak you're trying to measure. So here we can actually see where the gas plume is going. So you can have a more comprehensive measurement, a more accurate measurement, in so much as you can, exactly follow the gas and see where it's going. From a safety point of view, you can avoid being in the plume, which is sometimes the case when you're using other instruments. With your PIR or TVA type devices, you're going to struggle to, for example, in this image, you're looking at the wrong side of where the prevailing wind's going. So you're not going to get as accurate or comprehensive a reading as you might do being able to see that leak. And of course, the obvious factor is things you can't get to. So if something's high up or in an awkward position and you can't physically get to it with your other devices, then it's going to remove the need for scaffolding or another means, cherry picker or whatever, to get you up to that emission point. So the benefits of quantitative OGI. So when you're looking at two images on a camera who've been set up by maybe different technicians, they record the image, you can see varying responses based on the settings of the camera. So in this case, we're actually looking at the exact same emission. And if we compare the two, there's been some thermal tuning going on the left-hand image. So it has embellished the gas and made it look as if it's a larger leak than perhaps the other image looks. So it can be misleading when you're looking at the same image. So by quantifying that particular leak, then you can say for sure what you've got, what you're looking at. So changing the dynamic range, so that's your level and span, sometimes may make it look more dramatic. So because we're measuring the change in intensity of the pixels in the field of view, we will get the exact emission rate of the gas. So there are three important factors of the QOGI triangle, if you like. Delta T must be radiant contrast, as I said, at least 2 degrees greater, but the greater the delta T, the better. A consistent background also helps. If you've got clouds and stuff moving out in the background, this tends to give us spurious readings. The response factor, you see, the propane here is darker, and it's because it has a higher absorption factor within the camera filter. But in actual fact, it's the same size of leak as the methane. So it looks worse than it is. So by quantifying, we can get some more accurate results. And of course, the presence of gas concentration within the same response factor. So the better the response you'll get. And of course, like any instrument or technique, there are limitations. It's not going to be the most suitable thing for the best job. On a really windy day, for example, it's not a valid technique. And there are other considerations as well. But depending on your application and your lens availability, etc., what you've got at your disposal, potentially you can look at distances up to 210 feet with one of these 6-degree lenses. So it can have, for certain applications, can be a very valuable addition to your toolbox. Another reason for quantification, of course, is the regulatory stuff. There are many different regulations depending on where you are and who you work for. They can vary dramatically. Currently in the UK, we're kind of in between regulations. We're actually stating American. EPA is American agency, so our EA pretty much are doing the same stuff. I think we're between the European regs and committing to our own at the moment, and they're working on it. I believe UCAS is going to be rolling something out probably next year now, I would imagine. But it's definitely coming, and all UK operators will be expected to be compliant within a couple of years, I imagine. So to date, as long as you've had some sort of LDAR system in place as an operator, you were compliant. But I think those days are coming to an end, and we're all going to have to fall in line with the new or more or less the same as the European regulations, I would imagine. So applications then, there are many. I've chosen a couple of the more interesting ones to look at today. We all know about this sort of standard oil and gas refinery type, applications. So I'm going to look a little bit. It's kind of overlooked and a bit more specialized is furnace applications. So using the cameras for gas-fired quantitative and qualitative applications. So first thing is measurement, of course, temperature measurement. It's notoriously difficult to get all your values correct, and I can't really I can't really go into too much detail about furnace temperature measurement. I don't think we've got enough time for that today. But it's also a qualitative OGI application, and it's made easier, of course, by the use of filter. Now, the GO9 uses a special filter. In this case, we're actually looking for the least absorption from our filter. So you saw with the VOC camera, we wanted to have the maximum absorption possible, which was our 3.2 to 3.4. So in this case, we're looking at the point in the wavelength of a clean gas flame where it's least absorbed. And what that does is it makes our clean gas flame in our furnace appear almost invisible to the camera. So it blocks out that particular wavelength and makes the flame disappear more or less. Here we have an example. So on the left-hand side, we've got a nice optimized image. We've got no smoke to be seen. And in this situation, which is quite rare in my experience, we would be able to be very confident with our temperature measurement in this environment. On the unoptimized side, of course, we're able to see the flames, and these can have an incredible difference, can make an incredible difference when you're trying to measure any sort of temperature, and you just can't measure it, basically. They are almost impossible. And this is due to, it could be dirty fuel or, unoptimized burners, that type of thing. But there's lots of things can affect it. But what we're looking for is a optically resolved image, as we see on the left. So here we have a couple of qualitative thermography examples. So again, we've filtered out that gas flame, and we're able to get some really nice clear images. On the left-hand side, we've got a pretty pattern of scaling, and on the right, we've got the beginnings of evidence of coking within the pipe. So filtering out the flame allows us to visualize these different anomalies on the furnace tubes, which is useful information for the operators. So moving on then, we're going to look at some of our GIS applications, so gas insulated switchgear. It's the same story. This time, of course, we want a maximum absorption, and this is for looking at mainly SF6, but we can look at other stuff with this camera. And the filter in this case has been maximized for absorption is roughly 10.7 micrometers. And I'll have a look at a couple of examples here. We are going here. You have to look very carefully. And this example is where we've got a poor gas triangle. We've got one of our elements, which is our radiant contrast with our background, is missing. So it can make it very difficult to see. If you look carefully, you can see it now in high sensitivity mode, but prior to that, it was near invisible to the eye. It is quite a small leak, 6.8 kilograms over a 4-month period. But it was hard to see with the low radiant contrast due to the vegetation. In contrast then, it's the same size of breaker, but we have a very good background contrast. And of course, for our triangle, we've got a very good response factor with the gas as well. So it's a larger leak, of course. So another extreme is low pressure, and often these SF6 units are relatively low pressure. And as we can see here, sometimes changing the color palette to a high contrasting palette improves our ability to see that gas in certain circumstances. So this example, this was high voltage switchgear, and they were able to remove the panel. They obviously isolated the switch. Now, there was a gauge on the outside of the panel that showed a 0.4 bar drop in pressure over a 6-month period. So it was a very small emission. They isolated the switch and it was given access, roughly 6-inch opening at either side of the switch to be able to check this copper system. Now, because of the environment, we had one of our elements of our triangle was missing, the contrast, very low contrast environment. All the metallic parts were the same temperature. So in this case, we had to manipulate the environment by using my hand to heat up the pipework and leaving that residual trace of heat on the pipe. And that allowed us to visualize that very small emission. So quite a tricky one, but just to give you an example of how sensitive the cameras are and the size of emissions that can be detected if you are able to create those 3 parts of the triangle. So aerial applications then, we are just going to show you some, I mean, there's some good examples here. Now, I'm not saying that this aerial application mitigates the need for boots on the ground, but for specific applications and in the correct environment, it definitely has its advantages. So we're just going to show you some examples of these things. This was just quite a cool video I liked. The unit's mounted with a GF300A camera. In this video, we're using a T650 to check the temperature of the motors as the ambient temperature was nearing 40 degrees. This was out in Abu Dhabi. We were worried that they might be overheating during the survey, so we were just testing them prior to doing it. It was a flare tip inspection, so again there was radiant heat to consider. So the manufacturer's maximum recommended temperature for the motors was 60 degrees. So we were a bit concerned about that, but as it happens, they were fine. They were being kept nice and cool with the propellers, so it wasn't a problem. That was just for interest, really. So aerial thermography can also be qualitative. So things like flare burner temperatures are crucial, to the life of the flare. If they're being overheated, then that can have a significant impact on the lifetime. Again, for certain applications, in this case, we've got a leak on the roof of a storage tank. Now, you might have picked this up from the ground. You might have seen the gas, but you're not going to have seen where it was coming from. So there are certainly some advantages from doing aerial surveys as well. And in this case, it was definitely an advantage, although I do think it's just a vent we're looking at. So it's probably just stuck open. It's not that big an issue, but nevertheless, it's a reasonable example. So this one was a cracker. This is a large leak detected by a flow instrumentation. So they knew they had a leak. It's from a helicopter, so I apologize for the mad jumping about. But you get the idea. You can see it very clearly. So this is buried pipeline, and the chopper was brought in to fly over a greater distance of pipeline. But of course, this could be very easily done with a drone as well, and you're going to get a more stable and resolved image with that type of equipment. I suppose if you have to cover many miles of line, then that's going to be a helicopter's going to maybe be a better choice. This one is really just for an extreme example. So it's underwater venting and a drilling platform. Now they are allowed to do this bizarrely, but it's well regulated and permitted. So again, this is footage from a helicopter, but it just shows it very clearly coming out there. And that's about it from me, I think.